Assalamualaikum warahmatullahi wabarakatuh. And my name is Muhammad Iqmal. And my ID number is TH19014.
Okay, in this video, me and my friend, which is Syahmi, Aiman and HAZIM, we will present about chapter 5, which is mass and energy analysis of control volumes. Okay, for the first thing first, we look into the objective of this chapter. The first one is to develop the conservation of mass principle. The second one is to apply the conservation of mass principle to various systems, including steady and unsteady flow control volumes. Next is to apply the first law of thermodynamics as the statement of the conservation of energy principle to control volumes. Next is to identify the energy carried by a fluid stream crossing a control surface as the sum of internal energy, flow work, kinetic energy, and potential energy of the fluid, and to relate the combination of the internal energy and the flow work to the property enthalpy. Next is to solve the energy balance problem for common steady flow devices such as nozzles, compressor, turbines, throttling valve, mixing chamber, and heat exchanger. And the last one is to apply the energy balance to general unsteady flow processes with particular emphasis on the uniform flow process as the model for commonly encountered charging and discharging process. Okay, next is 5.1 conservation of mass, which is me myself Muhammad Iqmal bin Nizam will present it. The conservation of mass principle is one of the most fundamental principles in nature. We are all familiar with this principle and it is not difficult to understand. A person does not have to be a rocket scientist to figure out how much vinegar and oil dressing will be obtained by mixing 100 grams of oil with 25 grams of vinegar. Even chemical equations are balanced on the basis of the conservation of mass principle. When 16 kg of oxygen react with the 2 kg of hydrogen, 18 kg of water is formed. In the figure 5.1, as you can see here, mass is conserved even during chemical reaction. In an electrolysis process, the water separates back to 2 kg of hydrogen and 16 kg of oxygen. Technically, mass is not exactly conserved. It turns out that mass m and energy E can be converted to each other according to the well-known formula proposed by Albert Einstein in about 1879 to 1955, which is E equal to mc squared, where c is the speed of light in a vacuum, which is c equal to 2.9979 times by 10 power of 8 meter per second. This equation suggests that there is equivalence between mass and energy. Okay, next we look into the mass and volume flow rates. The amount of mass flowing through a cross-section per unit time is called the mass flow rate, and it's denoted by m dot. The dot over a symbol is used to indicate time rate of change. A fluid flow into or out of a control volume, usually through pipe or ducts. The differential mass flow rate of fluid flowing across a small area element DAC in a cross-section of a pipe is proportional to DAC itself. The fluid density ρ and the component of the flow velocity normal to DAC, which we denote as Vn, and it expressed as figure 5.2. The normal velocity Vn for a surface is the component of velocity perpendicular to the surface. Delta m0 equal to rho v and dAc. Note that both delta and d are used to indicate differential quantities, but the delta is typically used for quantities such as heat, work, and mass transfer that are path function and have inexact differential, while D is used for the quantities such as properties that are point function and have exact differentials. Okay, the next one is conservation of mass principle. The conservation of mass principle for a control volume can be expressed as the net mass transfer to or from a control volume during a time interval delta t is equal to the net change, increase or decrease, of the total mass within the control volume during delta t, that is, total mass entering the CV during delta t minus total mass leaving the CV during delta t equal to net change of mass within the CV during delta t, or m in minus m out equal to delta mcv in the kg, where delta mcv is m final minus m initial is the change of the mass of the control volume during the process, figure 5.5. The conservation of mass principle for an ordinary bathtub. It can also be expressed in the rate form as m dot in minus m dot out equal to d mcv divided by dt, where m dot in and m dot out are the total rate of mass flow into and out of the control volume, and dmcv divided dt is the rate of change of mass within the control volume boundaries. Okay, next is the mass balance for steady flow processes. During a steady flow process, the total amount of mass contained within a control volume does not change with time. MCV is constant. Then the conservation of mass principle required that the total amount of mass entering a control volume equal the total amount of mass leaving it. For a garden hose nozzle in steady operation, for example, the amount of water entering the nozzle per unit time is equal to the amount of water leaving it per unit time. When dealing with steady flow processes, we are not interested in the amount of mass that flow in or out of a device over time. Instead, we are interested in the amount of mass flowing per unit time, that is the mass flow rate m dot. The conservation of mass principle for a general steady flow system with multiple inlets and outlets is expressed in the rate form as figure 5.8, which is the conservation of mass principle for two inlet and one outlet steady flow system. Steady flow system is total m dot in equal to total m dot out, which is in the kilogram per second. It states that the total rate of mass entering a control volume is equal to the total rate of mass leaving it. Many engineering devices such as nozzles, diffuser, turbine, compressor, and pump involve a single stream, only one inlet and one outlet. For this case, we typically denote the inlet state by the subscript 1 and the outlet state by the subscript 2 and drop the summation signs. Then equation 5.18 reduce for single stream steady flow system to steady flow single stream equal to m dot 1 equal to m dot 2, which is rho 1 v1 a1 equal to rho 2 v2 a2. Okay, next we look into the example 5.1, which is the water flow through a garden hose nozzle. We look into this first question. A garden hose attached with a nozzle is used to fill a 10-gallon bucket. The inner diameter of the hose is 2 cm and it reduced to 0.8 cm at the nozzle exit. If it takes 15 seconds to to fill the bucket with the water, the first question is determine the volume and mass flow rate of water through the hose. And the second question is determine the average velocity of water at the nozzle exit. Okay, the solution. A garden hose is used to fill a water bucket. The volume and mass flow rate of water and the exit velocity are to be determined. Assume that water is a nearly incompressible substance and the flow through the hose is steady and there is no waste of water by splashing. The properties is we take the density of water to be 1000 kg per meter cube, which is equal to 1 kg per liter, and nothing that 10 gal of water are discharged in 15 seconds. The volume and the mass flow rate of water are V naught equal to V divided by delta T, which is time, equal to 10 gal over 15 seconds times by 3.7854 liter over 1 gal. And we use the calculator to get 0.757 liter per second. We time the 3.7854 over 1 gal to get this unit, which is liter per second. And next, m dot equal to rho v dot, which is 1 kilogram per liter time by 0.757 liter per second, and we get the answer is 0.757 liter per second, which is the mass flow rate of water. And next, we look into the cross-sectional area of the nozzle exit, which is area equal to pi r cube, which is pi times 0.4 centimeter cube. We get 0.5027 centimeter cube, and we convert it into meter cube, which is 0.5027 times by 10 power of negative 4. We get the meter cube. The volume flow rate through the hose and the nozzle is constant. Then the average velocity of water at the nozzle exit become V equal to V dot over A, which is area, which is 0.757 liter per second over by 0.5027 times 10 power of negative 4 meter cube, and we time with 1 meter cube over 1000 liter. We get the answer, which is 15.1 meter per second. This is the velocity of water at the nozzle exit. And in discussion, it can be shown that the average velocity in the hoses is 2.4 meter per second. Therefore, the nozzle increases the water velocity by over 6 times. Okay, that's all my part, and my other friend will present the other part. That's all from me. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Aiman bin Zolkifli. My ID metric is TH19013. We are from Group 1. Today we will learn about 5.2 subtopic, which is flow work and the energy of a flowing fluid. This work is known as the flow work or flow energy and is necessary for maintaining a continuous flow through a control system. Unlike closed system, Control volume involve mass flow across their boundaries, and some work is required to push the mass into or out of the control volume. In figure 5.12, it is a schematic for flow work. V is for the volume, P pressure, M mass, L length, F force, A area, and the imaginary piston at the initial value of the force. The force applied on the fluid element by imaginary piston is F equal to PA, where P is the fluid pressure and A is a cross-sectional area of the fluid element. You can refer to the figure 5.13 to see the force applied on the piston by the fluid. To push the entire fluid element into control volume, the force must act through a distance L. The work done in pushing the fluid element across the boundary is W equal to FL equal to PAL equal to PV. The flow work per unit mass obtained by dividing both sides of equation by the mass of the fluid element. W equal to PV and the unit is kilojoule per kg. The flow work relation is the same whether the fluid push into or out of the control volume. For example, you can refer to the figure 5.14. It have a workflow before entering and the workflow after entering. So the flow work is the energy need to push a fluid into or out of a control volume, and it is equal to PV, where P is pressure and V is volume. The total energy of flowing fluid. We can divide it into two types of the energy. For non-flowing fluid or a steady state, the formula is theta equal to H plus kinetic energy plus potential energy. The non-flowing fluid has three parts, which is internal energy, kinetic energy, and potential energy. While for the unsteady state or flowing fluid, the formula is theta equal to PV plus U plus kinetic energy plus potential energy. The unsteady state is the flowing fluid has four parts. The firstly is internal energy, kinetic energy, potential energy, and it has a flow energy that make the movement of the object. Energy transport by mass. The first formula is for the amount of energy transport, and the second formula is the rate of energy transport formula. Theta is a total energy per unit mass. The total energy of flowing fluid of mass is simply m theta where the properties of the mass is uniform. When fluid stream with uniform properties, the rate of energy flow with that stream is also m theta. When the kinetic and potential energies is negligible, these relations imply to E equal to mh, where m is mass and h is height. The unit of the energy is kilojoule. That's all in the 5.2 subtopic, which is flow work and the energy of flowing fluid. We continue in the 5.3 subtopic in the other slide. Thank you. We continue our lesson in 5.3, Energy Analysis of Steady Flow System. The fluid flows through a controlled volume steadily. The steadily means no change with time. So, for example, many engineering systems such as power plant operate under steady condition. Other than that is nozzle, turbines, and also compressor. A steady flow process. In steady flow process, fluid properties can change from point to point in the control volume. At any point, they remain constant during the entire process. No intensive or extensive properties within the control volume change with time. So, the volume, mass, and total energy remain constant. You can refer figure 5.19 for the example. At inlet or exit, the fluid properties also remain constant at fixed points, including velocity and elevation. For the example, you can refer in figure 5.20. So, heat and work interaction between a steady flow system and its surrounding do not change with time. Thus, power delivered by system and the rate of heat transfer to or from a system remain constant during steady flow process. Okay, for the mass balance, the formula is total mass in equal to total mass out. The mass formula is rho VA, where rho is the density, V is volume, and A is a cross-sectional area. In figure 521, it is an example of steady flow operation using water heater. Cool water stream with a mass flow rate continuously into water heater. So the hot water stream with the same mass flow rate flowing out of the water heater for us to use the hot water. It's losing heat to the surrounding air, and the electric heating element supply electrical work while heating process to the cool water. So the water will warm and the total energy will increase. For the energy balance, the formula is energy in equal to energy out. The rate of net energy transfer in by heat work, and mass equal to rate of net energy transfer out by heat, work, and mass. You can see the formula, that is Q in plus work in plus total mass in equal to Q out plus work out plus total mass out. In the thermodynamic, unit is very important. So at very high velocities, small change in velocities can cause significant change in the kinetic energy of the fluid. Under steady operation, shaft and electrical are only form of work a simple compressible system may involve. WE is the electrical work done and WSH is shaft work done. The unit meter squared per second squared and joule per kilogram are equivalent. That's all from me, Muhammad Aiman bin Zolkifli.
Assalamualaikum warahmatullahi wabarakatuh. My name is HAZIM bin MUHAMAD ROSLI, TH19016. I will present about application of steady flow in engineering devices. The first device is nozzles and diffuser. Nozzle and diffuser are commonly used in jet engines, rockets, spacecraft, and even in garden hose. So what is nozzles? Nozzles is a device that increases the velocity of a fluid at the expense of pressure, while a diffuser is a device that increases the pressure of a fluid by slowing it down. So nozzles and diffuser, the rate of heat transfer is very small because it's almost zero, and also it involves no work, and the velocities inside the nozzles and diffuser is very high. Next device is turbine and compressor. So the compressor will gather the air from outside for combustion, and the steam produced from combustion will pass through the turbine, and the work will be done against the shaft. The shaft will rotate and the turbines will produce electricity. So compressor are a device used to increase the pressure. So turbines and compressor, the heat transfer is usually negligible because it's also almost zero, and potential energy is also negligible. The velocity inside the compressor is low while in turbine is very high. And the last device is throttling valve. Throttling valve are devices that cause large pressure drop in the fluid. The pressure drop in fluid is followed by a large drop in temperature. So the throttling valves can be found inside a refrigerator or air conditioning application. So for throttling valve, there is no work done and no change in potential energy. Okay, so thank you.
Hello and good day to everyone who watched this video. My name is Ahmad bin Tajarazhar with the matrix number of TH19006, and not forgot to say hello sir. Thank you for watching this video. Today I'm going to talk about energy analysis of unsteady flow process, which is chapter 5.5 in the thermodynamics. Okay, during a steady flow process, no changes occur within the control volume, but this is not the case with the unsteady flow. Because when unsteady flow process is analyzed, it is important to keep track of the mass and energy contents of the control volume as well as the energy interaction across the boundary. This is some example of the unsteady flow process. The charging of rigid vessels from supply line, discharging a fluid from a pressurized vessel, driving a gas turbine with pressurized air stored in a large container, inflating tires of balloons, and even cooking with an ordinary pressure cooker. Unlike steady flow process, unsteady flow process start and end over some infinite time period instead of continuing indefinitely. Therefore, in this section, we deal with changes that occur over some time interval, which is delta t, instead of with the rate of change per unit time. An unsteady flow system in some respect is similar to a closed system, except that the mass within the system boundaries does not remain constant during the process. Another difference between steady and unsteady flow system is that steady flow systems are fixed in space, size, and shape, which is unsteady flow system, however, are not. They are usually stationary, which is not moving. That is, they are fixed in space, but they may involve moving boundaries and thus boundary work. The mass balance for any system undergoing a process can be expressed as you can see, the m in mass in equal to m out equal to m in minus with m out equal to m delta m system in kilogram, which is the mass. Is where delta m system equal to m final minus m initial is the change of the mass system. For control volume, it can also be expressed more explicitly as mi minus with me equal to m2 minus m1 cv, where I is inlet, e as exit initial state, and 2 final state is the control volume. Often or one or more terms in the equation above are zero. For example, mi, which is m inlet, equal to 0 if no mass enters the control volume during the process. Me is 0 if no mass leaves, and m1 is 0 if the control volume is initially evacuated. The energy content of a control volume changes with time during the unsteady flow process. When analyzing an unsteady flow process, we must keep track of the energy content of the control volume as well as the energies of the incoming and outgoing flow streams. The general energy balance was given earlier as energy in equal to energy out minus energy out equal to energy system in kilojoule. The initial and final properties of the control volume can be determined from the knowledge of initial and final states, which are completely specified by two independent intensive properties for simple compressible systems. Then the energy balance for a uniform flow system can be expressed explicitly as Q in, which is heat, I think, with W in, work in, plus with delta in, m theta, minus with Q out, W out, delta out, and m theta, equal to me m2 e2 minus with m1 e1 system, where delta equal to h plus ke plus pe is the energy of fluid stream at any inlet or exit per unit mass, and E equal to U plus KE plus PE is the energy of the controlled non-flowing fluid within the control volumes per unit mass. When the kinetic and potential energy changes associated with the control volume and fluid streams are negligible, as well as as is usually the case. The energy balance above are simplified to Q minus W equal to delta MAH out minus with delta in MH in plus with M2 U2 minus with M1 U1, where Q is Q net in equal to Q in minus Q out, which is Q can be simplified with Q equal to Q in minus Q out is the net heat input, and W is equal to W out minus W in, which is the work output, net work output. Note that if no mass enters or leaves the control volume during the process, ME equal to 0 and M1 equal to M2 equal to M. This equation reduces the energy balance for relation for closed system. Now we can see some example. The question said a rigid insulated tank that's initially evacuated is connected through the valve of supply line that carries steam at 1 megapascal and 300 degrees Celsius. Now the valve is open, the steam is allowed to flow slowly into the tank until the pressure need reaches 1 megapascal, at which point the valve is closed. Determine the final temperature of the steam in the tank. First, a valve connecting an initially evacuated tank to a steam line is open and steam flows in until the pressure inside rises to the line level. The final temperature is the tank to be determined. And here we can make assumption that this process can be analyzed as a uniform flow process, since the properties of the steam entering the control volume remain constant during the entire process. The kinetic and potential energies of the stream are negligible. Ke Pe is equal to 0. The tank is stationary, thus its kinetic and potential energy changes are 0. That is delta Ke equal to delta Pe equal to 0, and delta E system is equal to delta U system. There are no boundary electrical or shaft work interaction involved. The tank is well insulated, thus there is no heat transfer. This is Q, there's no Q. We take the tank as the system in this picture right here. This is the control volume. Since the mass crosses the system boundary during the process, we observe that there is an unsteady flow process since changes occur within the control volume. The control volume is initially evacuated, thus M1 equal to 0 and M1 U1 equal to 0. Thus there is one inlet for and no for exit mass flow. So this is the formula that we have shown. M in equal to M out equal to delta M system. So since M1 is 0, we can cancel that out. So M1 is equal to M2, I guess. Yeah. And this is the energy balance which is shown above, which is E in equal to E out equal to E system minus E out. E in minus E out equal to E system. MH1 equal to MH2 U2, since Q equal to 0, KEPE equal to 0, and M1 equal to 0. Combining the mass and energy balance given, this is, I think they just cut it out. MM is both sides as M, so U2 equal to H1. That is the final internal energy of the steam tank equal enthalpy stream entering the tank. The enthalpy of the stream can be stated as P1 is 1. This is you can find this is which students can find in the periodic table. I mean the table on the real far in the book, I think. So P1 is the pressure was given. The temperature it was given. This is P1 with the initial temperature and the initial pressure, and then from that you can find the H1, which is the enthalpy, which is equal to EU2. Since we already find this, and since U2 equal to H1, you can conclude that that this number is equal to U2. Since we have the pressure and we have the U, we can find the T also from the table. So we can, so that's all from me. So I hope you can understand. Just ignore my bad English languages. Okay, thank you.
Thank you for watching, and don't forget to stay home and stay safe.